Hi everybody, this video is going to talk about trigonometric identities and how we are going to use them in our class. So basically, the definition of a trigonometric identity is an equation involving trigonometric functions that is true for all values for which every expression in the equation is defined. So when you are given a trig identity, you can assume that for everything we're going to be working on, that those equations are true all the time and you can always use them. We're going to be using these identities to help evaluate functions, simplify expressions, verify identities, and solve equations. The first type of identities that we're going to be talking about are the quotient identities and the reciprocal identities. So the quotient identities, we've talked about in passing when we made the unit circle, when we've talked about sine and cosine, but basically it tells us that tangent is equal to sine over cosine. If we know that tan is sine over cosine, we also know that its reciprocal cotan would be equal to the reciprocal, the original function, therefore cosine over sine. The reciprocal identities down here at the bottom are ones that we talked about from the very beginning. When we first talked about sine, cosine, and tangent, we talked about that those trig functions have these reciprocal identities, meaning that they're the same thing. So sine we know is equal to 1 over cosecant, or cosecant is equal to 1 over sine. They go hand in hand. So the reciprocal identities you guys have already seen, now we're just going to start using them. So for the next few problems, we're going to be finding trig values. In the past, when we've seen a problem like this, something like if cosecant is equal to negative root 30 over 3, we would have said, okay, well, we know the cosine is this. We're going to draw the triangle and solve for it. But now what we're going to do is simplify it a little bit, I think. I think our approach now is going to be easier, that we're going to use identities to find the values, to find the trig values, rather than using trig information that we're given to draw triangles and find the information from the triangles. So let's get into the examples and I'll show you what I mean. So for number one, if we know that the secant is equal to negative root 30 over 3, we're looking to find cosine. Well, we know that cosine, based on its reciprocal identity, is equal to 1 over secant. So we can substitute the secant that we have right in for it. So cosine is equal to 1 over the secant, or 1 over negative root 30 over 3. We're going to solve this by keep, change, flip. So we have 1 times the reciprocal, negative 3 over root 30. Now we need to rationalize this. We can't have a radical in the denominator, so we're going to rationalize by multiplying by the root 30 over root 30 to give us negative 3 square root of 30 over 30. Now we can simplify this a little bit. 3 goes into 3 once, 3 goes into 30, that stays as a 10. So our final answer for this problem is negative square root of 30 over 10. So no triangles necessary. What we're doing is we're using what we know from our trig identities, in this case, that the cosine is equal to 1 over the secant. And instead of drawing the triangles and finding our trig values that way, we're going to do it in a more algebraic approach. So hopefully that makes sense. If it does, feel free on the next example to pause the video and give it a try. Otherwise, stick with me and we'll go through it together. Number 2 says that if tangent of x is square root of 2 over 4 and cosine of x is negative 2 square roots of 2 over 3, it's asking for us to find the sine of x. So here we're given two pieces of information, tangent and cosine, and we're asked to find sine. So what we want to do is we want to approach this problem saying, what do we know? And therefore, how am I going to find what I'm looking for? So tangent, if we think about the tangent basic identity, we know that the tangent of x is equal to the sine of x over the cosine of x. Now we have two pieces of information out of these three that we can fill in. So tangent we know is the square root of 2 over 4. Sine is what we're looking for. And we have that the cosine is negative 2 square roots of 2 over 3. So when we're trying to solve for this, we want to isolate the sine of x. So we're going to multiply both sides by negative 2 square roots of 2 over 3. And when we do that, we're going to find that, I'm actually going to rewrite the whole thing, that the sine of x is equal to square root of 2 over 4 times negative 2 square roots of 2 over 3. And that equation previous, this is our entire denominator, so it will cancel out completely. So now we're going to have to multiply across. So square root of 2 times the square root of 2 gives us 2, so that becomes negative 4 over 12, which is just equal to 1/3. So the sine of x, what we're asked to find, is equal to negative 1/3. Final answer. Sometimes when we're trying to solve values or solve for values using trig identities, sometimes the approach isn't necessarily clear when you're given the problem and how to get to where you're going. What I would suggest doing is writing what you know, and then often you can work off of that. When we're using trig identities, if you can turn things directly into sine and cosine, those are more relatable. Those are the trig identities that we're more familiar with as opposed to the reciprocal identities. So for number 3, it says if cosecant of beta, that's our Greek letter beta, is 7 over 3, and cotan of beta is negative 2 square roots of 10 over 3, find the secant of beta. So to make this easier on myself, I'm going to start by saying that if I know the cosecant of beta is 7 over 3, that tells me that the sine of beta is 3 over 7. Okay. If I know that the cotan of beta is negative 2 square roots of 10 over 3, then the tan of beta is equal to negative 3 over 2 square roots of 10. What I'm going to do now is very similar to the last problem, use that quotient identity, that tangent is equal to sine over cosine. I'm going to find cosine and then just convert it into secant. You may have a different approach, and if you do, that's totally fine. As long as you end up with the right answer and you show your steps in terms of how you got there, it's totally great. Identities are kind of fun in that way, that you could have a number of different approaches to the same problem, still get the same answer, but it's okay to go on and do it your own way. So this is the way that I would approach this one. So I'm going to say that tan of beta equals sine over cosine. So I'm going to plug in what I have. I have negative 3 over 2 square roots of 10 equals 3 over 7 over cosine. Okay. What's interesting here, if you think about it, sorry, that should be beta, not theta, my apologies. If we multiply both sides by 7 over 3, that's going to get rid of this fraction in the top. And what I'm left with then is 1 over cosine, which actually is secant. So sometimes you even stumble across these as you do them. I was going to originally solve for the cosine of beta and then flip it. But because of the way this identity is set up, we have cosine of beta in the denominator. As long as we make the numerator 1, that automatically gives us the secant of b. So hopefully that makes sense. So what I'm going to do is just simplify on the left side of the equation here. 3 is going to cancel with 3. So I'm going to have that the secant of beta, I'm kind of switching sides here, equals negative 7 over 2 square roots of 10. I have to rationalize, so I'm going to multiply both the numerator and the denominator by the square root of 10 to give me negative 7 square roots of 10 over 20. The next type of trig identity that we're going to talk about is the Pythagorean identities. These, in my opinion, are your bread and butter of simplifying and verifying trig identities or trig expressions. The best part about the Pythagorean identities is that if you can get the right set of terms together, they're equal to 1. And if you can find that, if you can take out these two trig functions in an expression and instead just put in 1, it's going to make your simplification so much easier. So I consider these the bread and butter. Normally, I would say definitely memorize these, but I know we're all kind of working remotely, so feel free to have them in front of you too. Um, but not only do we have these three, where we have the cosine squared of theta plus the sine squared of theta equals 1, tan squared theta plus 1 equals secant squared of theta, and cotan squared of theta plus 1 equals cosecant squared theta. Not only do we have those three, but we also have the different iterations when we move the different terms around. So let me show you what I mean. So if we look at the first one, cosine squared theta plus sine squared theta equals 1. Well, we have that expression, we have that equation, we know that's true. But what I can also do is, for example, subtract sine squared theta from both sides. When I do that, what I have now is that the cosine squared theta equals 1 minus sine squared theta. So if we're simplifying an expression and you were to see 1 minus sine of sine squared theta, if you were to see this side of the equation, instead of having that, you could substitute in cosine squared theta. We go from having two terms to having one. So we have this iteration that we can use as well. If we were to look at another example, if we were to do the same idea, instead of subtracting sine squared theta from both sides, if I were to subtract cosine squared theta from both sides, then I would end up with sine squared theta equals 1 minus cosine squared theta. So again, if I have 1 minus cosine squared theta in an expression, I can take this out and substitute in sine squared theta to have one term instead of two. So these are really, really awesome things to look for. I'm going to do the same thing on the other two expressions. I'm going to move them around so we see the two other iterations. So for tan squared, for the second expression here, right now I have secant squared by itself. But what I can do is move the tangent squared over to have 1 by itself. So I also have 1 equals secant squared theta minus tangent squared theta. That's another iteration if I were to take the tangent and move it over. The other one that I can do is if I were to move the 1 over to have tangent by itself, then I would have that tangent squared theta equals secant squared theta minus 1. So again, this is just another expression that we can use. If we have secant and secant squared minus 1, we can substitute in tan squared. If we have secant squared minus tan squared, well, that's a super bonus because we can take those two trig expressions out and substitute in 1. Let's look at the last one. So we've got cotan squared plus 1 equals cosecant. Well, I can subtract 1 from both sides. So I'd have cotan squared theta equals cosecant squared theta minus 1. That's my second iteration of this expression. And then I can also leave the 1 by itself and subtract, if I go back to the original, subtract cotan from both sides. So I have cosecant squared minus cotan squared. So now when you're doing verification and simplification, these Pythagorean identities are all ones that you're going to want to look for. Question number 4 has us using Pythagorean identities to find the function value. So number 4 says find cosine of theta and tan of theta if the sine of theta is negative 1/3 and the cotan is less than 0. So what we need to start with here is to figure out where this angle actually is. So if we consider the unit circle again, if our sine value is negative, which it is, then the angle has to be somewhere below the x-axis. It has to be in quadrants either 3 or 4. What the question is also telling us is that the cotan of theta is less than 0. If cotan is less than 0 or negative, that also means the tangent is less than 0 or negative. Well, tangent is positive in quadrant 3, so that's not going to work. The angle that we're talking about has to be in quadrant 4. Now, this is important because the sign, sign, of our final answer for cosine should be, in this case, positive because we are to the right of the y-axis. So knowing what quadrant the angle is happening in, we don't have to draw the triangle anymore, but it's going to let us know what our values should be. Okay, so we're going to use the Pythagorean identities to solve for cosine and tan. So what we're going to do, I'm going to start with that the cosine squared theta equals 1 minus sine squared theta. So we know sine, right? That's the one that we're given, and we're trying to find cosine. So I took this first Pythagorean identity, cosine squared plus sine squared equals 1, and I subtracted sine squared from both sides. This allows me to solve for cosine without moving things around later. If you want to start with sine squared plus cosine squared equals 1 and then go from there, totally fine. I just like to have what I'm solving for by itself to get started. So cosine squared theta equals 1 minus negative 1/3 squared. Now remember, we've got to worry about those order of operations first. So this is equal to 1 minus negative 1/3 times negative 1/3 gives us positive 1/9. This really is 9 over 9 minus 1 over 9 to give us 8 over 9. The cosine squared of theta, let me rewrite, cosine squared of theta is equal to 8 over 9. So now what I'm going to do is take the square root of both sides to leave me with the cosine of theta is equal to the square root of 8 over the square root of 9. Now remember, these are plus or minus, technically both of them, but we already discovered that our angle is going to be in quadrant 4, so I know my cosine is going to be positive. So we can not even worry about the plus or minus anymore. We know cosine's positive. So if I simplify the square root of 8, I'm going to have 2 square roots of 2. If I simplify the square root of 9, I'm going to have 3. So the cosine of theta is equal to 2 square roots of 2 over 3. That's my final answer. The second part of the question is asking us to find tangent of theta. So for this one, I'm going to use the identity that the tangent of theta is equal to sine of theta over cosine of theta. I'm going to use this one because I know both of those values. Sine is negative 1/3. Cosine we just found is 2 square roots of 2 over 3. So again, keep change flip, negative 1/3 times instead of division, 3 over 2 square roots of 2. I'm going to cancel out the 3's to give me negative 1 over 2 square roots of 2. Now I have to rationalize, so I'm going to multiply both the numerator and the denominator by 2, or root 2. So I have negative square root of 2 over 4. Square root of 2 times square root of 2 gives me 2, times 2 is 4. So my final answer for tangent is negative square root of 2 over 4. And the negative makes sense because the original problem stated that the cotan of theta is less than 0. So it would make sense that tangent is less than 0, also because we know the angle occurs in quadrant 4. Number 5 is very, very similar to number 4. So if you did okay with the last problem, what I would suggest is for you to pause the video, give this one a try on your own, and then check back in after you finished your work. All right, so here's number 5. So we're looking to find tangent of x and sine of x, and we're given that the secant of x is 6 over 5. We're also given that the sine of x is greater than 0. So the first thing I want to figure out is which quadrant is this happening in? So if we know that the sine of x is greater than 0, we know that it's happening in either quadrants 1 or 2. Sine goes with y, so we need the angle to show that y is positive or above the x-axis. Now we also know something else. It's a little hidden. We know that the secant of x is 6 over 5. Well, if we know that the secant of x is 6 over 5, we know that the cosine of x is 5 over 6. We're given that number. We're given that the cosine is also positive. So that is going to be to the right of the y-axis. Cosine goes with x, right? It's our x-coordinate. So the only quadrant where both of those things happen is here in quadrant 1. The information's not always super clear. Sometimes you have to do a little bit of digging for it, so be on the lookout. So we know that both sine and cosine are positive, as is tangent. What's kind of nice here is we don't have to worry about the signs, SIGNs of any of the values. We know everything is going to stay positive. So we know cosine of x. We're using Pythagorean identities. We're trying to find tangent. So what we might want to do is we know secant, we're trying to find tangent. We're going to, what would make the most sense would be to use our second trig identity, this tan squared plus 1 equals secant squared theta. Now again, we know secant theta, we're looking for tan, so I'm actually going to rearrange this problem so that what we're looking for tan is by itself. So that's going to give us that the tan squared theta equals secant squared theta minus 1. I just subtracted 1 from both sides so that I could have tan squared isolated. Okay, so now I can plug in what I know. I've got that tan squared theta is equal to, we know secant is 6 over 5. The squared means we're actually going to square that whole thing, minus 1. So we get 36 over 25 minus 1. I'm going to turn that into 25 over 25 just to make it easier, which is equal to 11 over 25. So what I really have here is that the tangent squared of theta, or tangent theta squared, actually x really, equals 11 over 25. To solve for tangent, I'm going to take the square root of both sides, giving me that the tangent of x is equal to the square root of 11 over 5. From here, we're asked to find sine of x. So what I'm going to do, rather than using a Pythagorean identity here, because nothing really relates tangent and cosine or tangent and sine, we'd have to use all the reciprocal identities. I'm going to go back to an identity that we've already used, the quotient identity, that the tan of x is equal to the sine of x over the cosine of x. So I know tangent is square root of 11 over 5. Sine of x is what I'm solving for. Cosine of x is 5 over 6, we figured out earlier. So to get sine by itself, we're going to multiply both sides by 5 over 6. What's going to work out nicely here is the 5's cancel. So I'm left with that sine of x is equal to the square root of 11 over 6. Something new for this week is the next type of identities called the cofunction identities. Basically, and I'm going to prove this to you once, you don't have to remember how to prove it, but the cofunction, so if we think about sine and cosine, right, those two are going to go together. If we think about tan and cotan, those two identities go together. And if we think about secant and cosecant, those two identities go together. So that's kind of your hint on how to remember which ones go with which. But basically what it's saying is that if we have the sine of an angle, if we look at this one first, if we have the sine of an angle, then we also have the cosine. It's going to have the same cosine as if we subtract pi over 2 minus theta, minus that angle. So it's a little weird to kind of talk through with words. I'm going to show you how it works with one example. So say for a second that we have the cosine of pi over 6. Okay, let's go back to our unit circle. I'm just going to draw quadrant 1 for now. Pi over 6 is that first angle here. If we think back to our coordinates, we know that the cosine is the square root of 3 over 2, and the sine is 1/2. Okay, so the cosine of pi over 6 is the square root of 3 over 2. What this cofunction identity tells us is that if we have the cosine of theta, that's saying that the sine of pi over 2 minus that original theta, in this case pi over 6, should also be the square root of 3 over 2. Okay, well, let's see if that's true. So if we have pi over 2 minus pi over 6, well, we need common denominators to multiply, or to subtract rather. So I'm going to multiply that first fraction by 3 over 3. So now I have 3 pi over 6 minus pi over 6. Now I can subtract those two, and I end up with 2 pi over 6, or just pi over 3. So this now can be substituted back in here. This is saying that the sine of pi over 3 should be equal to square root of 3 over 2. Let's see if that's true. So back over on our graph, on our unit circle, pi over 3 is this angle up here. And if we either remember the left-hand trick or we just memorize, we know that the sine of pi over 3 is 1/2 and the cosine is the square root of 3 over 2. So the sine of pi over 3, the y value, is in fact the square root of 3 over 2. The cosine of pi over 6 matches up with the sine of pi over 2 minus the angle we were working with. If we go about it the other way, the sine of pi over 6 is equal to the cosine of pi over 2 minus the angle we're talking about, or in this case, pi over 6, and they do match up. So again, I'm not asking you to memorize these, I'm just showing you where it comes from. But if we're working with identities that has something like the cosine of pi over 2 minus theta, we don't want to deal with that. We can take that out and substitute in instead the sine of theta. So it kind of works out nicely in terms of getting rid of kind of big bulky expressions and plugging in ones that are a little more simple and straightforward. The last grouping of identities for this video is going to be our even-odd identities. This has to do with the signs, the SIGN, of different trig functions. So what you'll notice is if we take the sine of a negative angle, that we can transform into negative the sine of the angle. That same pattern holds true for tangent, that if we have the tan of a negative angle, it's the same as negative the tan of the angle. And, but if we look at cosine, when we're taking the cosine of a negative angle, what that's saying is it's actually equal to the positive cosine of that angle. So I'm going to show you in a couple different ways why this is true. What you need to remember is that cosine functions are even, and tan, cotan, and sine and cosine are odd. That's going to help you remember. So in terms of even and odd functions, we talked about them at the beginning of the year. Odd functions have symmetry about the origin. So an example of an odd function would be something like x cubed, where it has a function that looks like this. So the best way to think about this is if I'm taking an x value out here, I have a positive y value, positive x, positive y. But if I go the same distance in the negative direction, my negative x produces a negative y. Okay, so the negative input produces the negative output. Or if we have f of x, that's going to give us y. But if we do f of negative x, that's going to give us negative y. So this is our positive x, positive y, or negative x, negative y. Whereas an even function was something like x squared. Even functions have symmetry about the y-axis. So that would be something like a quadratic here. So in this case, if we go out to x over here, we have a positive y. If we go negative x the same distance, we still have that same positive y value. So you can kind of think about it the same idea with our functions as our trig functions. So f of positive x gives us y, but f of negative x also gives us y. Okay, so that's the way of looking at it from a function perspective. If we were to look at it in terms of the unit circle, if we think about a negative angle here, this is our negative theta. The sine value is our y value. We've got x and we've got y, and sine is y. Well, the negative value of the sine, so the y value of the negative angle, is actually the opposite of the positive angle. This is y, this is actually negative y. Whereas for cosine, we're talking about the x value, and here the x values are exactly the same. So if we're taking the sine of a negative angle, the y value of that negative angle is going to be the same number, just the opposite sign, SIGN, as the positive angle in quadrant 1. If we're thinking about cosine, if we're thinking about x, the values are exactly the same, whether we take the negative angle or we take the positive angle. So what this means is if we're given a negative angle with cosine, we can actually just ignore the negative altogether. If we're given a negative angle for sine, that means we actually have to take that negative out of the angle itself and just stick it in front of the actual trig sine expression. So I think that'll make a little more sense when we talk through some examples, but here's the basis as to why those are true. So here's the examples for our cofunction identities and our even-odd identities. We're going to use both of them in these. I put them up top. These identities I don't expect you to memorize at this point. If we were in school, different story, but for now, feel free to have them in front of you. So number 6 says that if the sine of negative theta equals negative 0.97, find the cosine of pi over 2 minus theta. So we've got a couple things going on here. Let's start with the equation that we're given here. If the sine of negative theta equals negative 0.97, what we can do is instead of saying sine of negative theta, we can take that negative and pull it out, just like we do in that even-odd expression, even-odd identity. So instead of writing the sine of negative theta, I'm going to write negative sine of theta equals negative 0.97. Well, what that means is then I can divide both sides by negative 1 to tell me that the sine of theta is actually equal to 0.97. So we just used the even-odd identity to simplify this sine of theta expression. The second piece of this is asking us to find the cosine of pi over 2 minus theta. Well, if we come up here, the sine of theta equals the cosine of pi over 2 minus theta. This equals the sine of theta. So the cosine of pi over 2 minus theta is the same as sine, which we've already solved for. Our final answer is going to be 0.97. Now, there could be different ways to approach this. Feel free to do it in a different order, but what we're doing is we're taking things that are a little more complicated and we're trying to write them in a little more simple fashion. Number 7 is similar to number 6. We're going to take what we have and try to make it a little more simple. So right away, we're given the tan of negative alpha, that's our Greek letter alpha, is equal to negative 2.36. So I'm going to come up to my even-odd identities, and I'm going to use this expression here, that the tan of negative theta is equal to the negative tan of theta. So I'm going to rewrite this as negative tan of alpha equals negative 2.36. Again, I'm going to divide both sides by negative 1 to tell me that the tan of alpha is equal to 2.36. Okay, so now we have to look at the second piece. The second piece of this tells us that the cotan of alpha minus pi over 2, that's what we're looking for. So I'm going to go up and I'm going to find my cotan expression. It's this one. But now we've got a problem. So this expression says that the tan of theta is equal to the cotan of pi over 2 minus theta, or alpha either way. That doesn't match. Cotan of pi over 2 minus theta does not match alpha minus pi over 2. Not the variable, but the order in which they're written. I will actually make this alpha just to make it a little bit easier. So the tan of alpha, which is what we're using in this problem, is equal to the cotan of pi over 2 minus alpha. But what we're asked to find is alpha minus pi over 2. So here's where things get a little bit tricky. We need to be able to use tangent. We just found tangent, and we need to be able to use it to solve for this expression. So we're going to take this cotan of alpha minus pi over 2 from the problem, and we're going to try to transform it into cotan of pi over 2 minus alpha. So what we're going to do here is if we factor out a negative 1 from this expression, this becomes a negative alpha, and this becomes a positive pi over 2. So what I have when I do that is the cotan of -1 times pi over 2 minus alpha. So I'm a step closer to where I want to be. Now, if we look back up to this expression, the cotan of a negative theta, so this is really our angle. The pi over 2 minus alpha is our angle. That's our theta, or alpha. If we look to that, we've got a negative inside. This identity right here tells us that we can take that negative and put it out front. So what we now have equal is negative cotan of pi over 2 minus alpha. This now matches up with what we know based on an identity. So, full circle, the tangent of alpha is equal to the negative cotangent of pi over 2 minus alpha. We know the tangent is 2.36, so we're going to go ahead and substitute that in here. Equals negative cotan of pi over 2 minus alpha. So to find that cotan of pi over 2 minus alpha, we have to divide both sides by -1, making our final answer of the cotan of alpha minus pi over 2 to be equal to the negative 2.36. This one is a tricky one. There's a lot of back and forth. The important piece here is that if we're asked to find something that's the opposite, we don't have that pi over 2 first, we have the alpha first, or the theta first, or the x first. You have to factor out a -1 in order to make it match up with those cofunction identities. So hopefully that makes sense. Go ahead back and watch it again if you need to. The last example for this video is number 8, and it says that if the secant of beta minus pi over 2 is equal to -3.62, find the cosecant of negative beta. So again, if we start looking with our cofunction identity right here, you'll notice that the angle and the pi over 2 are switched from the actual identity. So that's the one that we're going to use up here. So actually, second one. So what we're going to do is we're going to factor out a -1. So the secant of -1 times, now we've got pi over 2 minus beta equals -3.62. So for the second part of this, secant goes with cosine, in fact, in the idea that they're both even functions. So if we have the secant of a negative angle, instead of it being the negative secant of that angle, the negative just kind of goes away, the same as it would in a quadratic function with a parabola. It doesn't matter if we have a negative input, we're going to end up with a positive output. So this is actually equal to the secant of pi over 2 minus beta equals -3.62. So that's going to help us because we're going to use secant to then find cosecant. So if we use this identity up here, that the secant of pi over 2 minus theta, or beta, is equal to cosecant, then we know that this is actually equal to the cosecant of beta. So now we have a whole new expression. But the problem is we're not asked to find the cosecant of beta, we're asked to find the cosecant of negative beta. So if we want to know the cosecant of negative beta, we know that the cosecant of negative beta is equal to the negative cosecant of positive beta. That's what we're going to find right up here. So what we'd like to get is negative cosecant of beta by itself. If we have positive here, what we can do is actually divide both sides by -1 to give us a positive 3.62 on the left and a negative cosecant of beta on the right. So now we're a step closer. If we know that negative cosecant of beta is equal to cosecant of negative beta, I can actually substitute that in. So now I have 3.62 equals the cosecant of negative beta. And that is going to be my final answer. I'm looking for the cosecant of negative beta. That was what I was asked to find, and that is what I have. So that final answer is going to be 3.62. So that was a lot of information, you guys. I talked a lot about why some of these identities work. I just want to reiterate, I'm not going to ask you to produce those descriptions or those proofs. What I do want you to be able to do is get comfortable enough with these identities that when you see them in an equation, when you're asked to solve or simplify or verify, that you feel comfortable doing that, substituting one in for the next. I always find it to be really helpful to understand why things work and where they come from, which is why I put some of those details in this video. But again, you don't necessarily have to be able to reproduce those. Just be able to understand the identities, look for them in different problems, and then swap them out if necessary or if it makes sense. Please let me know if you have any questions. I hope this video was helpful. Bye.